It was very rather long. I think, okay, it was first of all, let me thank all of you, the team, starting right from the head and all our colleagues. I can see all of them there, Vaishali, Nanesh, and of course our own Professor Nagarajan, Professor Angwala. They're all there. So this, what I thought was going to be a very informal talk, and of course Nurada has spelled most of it. Yeah, we first met in 95 when we joined the department initially. But I would also here share something that when I was at TIFR, she said she was in TIFR during 1991. It is surprising, I didn't meet her, but I had met Raghav. So in her TIFR. So that was the time when I had returned after my maternity leave in 91. So essentially most of the work which was done, the first part was setting up the instrumentation, and it is that part that I'm going to share with you all now, you know, the journey, because essentially we are looking at some technique, most important technique in experimental condensed matter physics. So I think I'll just go over to showing the screen. I think, yeah.
Forgot.
Huh.
My research kept alive by
Huh.
UDP and Radha madam.
Okay, thank you, sir, for that.
The only research contribution I have is from Radha's group on with fluid.
Thank you, sir.
Radha. Thank you, Radha.
Sir. Okay. Yeah. So somehow I don't know why I got this very catchy title, and that I think I owe the time I joined TIFR. I was put in this group of low temperature physics, which was headed by late Professor Girish Chandra, and I started working with the other members were Professor Ramakrishnan, who's now presently the director, and then we had Dr. Ray, and then Professor Nigam, with whom I actually started doing the experimental work. And those days they were setting up a huge, big superconducting magnet. So the first part of it was just, you know, looking at it, and I was given the books to read. And the first most impressive book was the one by Lunasma, which said The Quest for Absolute Zero. And then when, as you started reading, you realize there was so much to it, you know, and it is again, when you say low temperatures or all this is not just confined to only condensed matter physics. It is true that a lot of material scientists use this technique quite a lot, but then you know that there are other area people who also use it, especially nuclear physics, astronomy, and so on. So this is a very important technique of in all experimental areas, and that I thought, you know, the towards zero was, because I didn't want to use the same order, I said, so let me sound it towards absolute zero. So what goes in it? Well, the quest itself is an interesting story, but along with the quest there are many other attachments or paraphernalia, which I put it all together under rest. There is, and if you will see that each one of it has a story in itself to say. And finally, the best is always, you know, superconductivity. Moment I say that, we have our own Professor Nagarajan there, and we had a lot of course, not that I particularly looked at any superconducting materials, because the time I joined TIFR, everybody was active with the high TC super. They called it the high TC boom. But I was away from that part, but nonetheless, you know, it has always been fascinating. And for this, let me, as I just put in my, it's not moving. Screen is, yeah. So I owe my gratitude. This is Professor Girish Chandra, who was headed in the group. And I would like here to say he has worked with all the best. He has, as again, Nagarajan reminded me, yeah, you have to mention that he had worked in Kapitza's lab. And when he joined TIFR, he set up a low temperature facility using the technique of what is called as adiabatic demagnetization. And let me tell you that this is nothing but this technique. Many of our, since most of them are students, MSc students present over here, so they will know that they have done this, at least the first year, studied what is meant by cooling of a paramagnetic salt. So they will know that This is a technique they must have heard about. And Professor Grishandra was the first to set it up in our country. And here, yes, you can see our lab. That's Professor Nigam and Professor Nagarajan himself over there with Professor Paulus. So I managed to, I said, last minute, I somehow got this picture. I said, yes, I should share it. So this is been my profile after I finished my MSc. I was very lucky to get selected for the PhD program at TIFR. And here I would like to first pay my on gratitude to all my teachers who have been in the department. Teachers, my own batchmates, some of whom are here in the department. Was that time Professor Rangwala was heading the department, Mr. Rohini Godbole, Mr. Gupta, Mr. Narsale, and yes, we had both Professor R.J. Kulkarni and Mr. V.H. Kulkarni, and then Professor Gogavle and Professor Yadav. They were all there in the department. So Varsha joined a year later. So the 85 when we joined, these were the teachers we had, some visiting teachers also. And here I would like to again particularly mention a late Professor T.R. Rao, who had, I would say, triggered that interest for superconductivity. He particularly taught that he was teaching part of solid state electronics and this part of solid state physics which had superconductivity. So, I was very enamored by that subject. We used to have very good, even now I think the library still has that books. There were very nice monographs. There's particularly one by Tinkham and then a very small one by Linton. So it was very interesting. It fascinated me. So this is the kind of, strength what a teacher has, it triggers. And I said, yes, this is something which I should be pursuing. And along with that, the following year, we had this experimental techniques, which Professor Bhattacharya was co-teaching along with other teachers. And low temperatures, magnets, these were some of the topics that figured over there. And of course, now we are having this, I don't know how much of low temperature techniques we are doing. So that is what I thought, I have been giving talks mainly on the recent research of all this nano materials and so on. But I thought, let me for this, it's not so much talking more about my work, but actually about my rich learning experience, which I have had both at the department and at TIFR. So these were some of the experimental techniques. That most of these are any material scientist would have to do. So my sample pressure, when I say arc melting, is because I was essentially working with metallic specimens. And there is a furnace, you have to wear all these dark glasses, like all these welder's glasses and so on. A very interesting experience in itself. And we looked at magnetic and transport measurements. So the range of temperatures between 2 Kelvin to 300 Kelvin, which means that you are going to low temperatures and the coolant which is being used is liquid helium. And liquid helium alone would not be enough. Most of the older cryostats used to have an outer nitrogen shield. This was essentially because, you can at least reduce the usage of liquid helium and, reduce the boil off, because in that, since nitrogen was is still, cheaper than liquid helium. And the magnetic fields up to 7 Tesla. So the first part of it was, though we had a very huge magnet which was imported, but it had to be sent back. And then Professor Nigam was known to be fabricating the superconducting magnet. He got the wire. So my first 2 years when we look at different projects, so this was one project which we embarked on, was binding the magnet. Now that itself is a topic in itself, and I thought I will show you the picture, but I will tell you at that time what kind of experience it was to wind the superconducting magnet. And it was only, I think, towards the end of my PhD when all the other, so initially I worked with a AC susceptometer which was designed and developed by Professor Ramakrishnan. And these were the instruments, whether vibrating sample magnetometer and SQUID, which came in a little later. Almost towards, I was finishing my work and when this came in. So most of my work was focused on looking at the AC susceptibility and transport and magnetoresistance measurements in the home-built superconducting magnet. So this was been my learning experience at TIFR. So these were some of the materials that I studied. Yeah, you can, as you can see, it's a very rich alloys, and this is what is called as a spin glass. So here again, I will not go into describing all this. It's a topic in itself. I want to focus more on the technique of low temperatures. So the other materials that I studied was this rare earths, and fortunately, of course, getting to back to work on this noble metal is still remains far off, but I still feel that there are a lot of work which could be done, at least a theoretical. I would here like to also say that during those days, Professor Press was a postdoctoral fellow at TIFR, and he had worked on some of these clusters. You know, when you are introducing a little bit of transition metal into a noble metal system, a very dilute concentration, go on increasing it, and then they start looking at how is the correlation of these electrons with each other, how do they, what kind of behavior they would show, and so on. And you talking about clustering phenomenon, and Professor Press had come up with some kind of a program to study into it, and we were trying to understand whether it would fit in. But then we had to also, you know, those days when we are doing experiments, you have to like make hay while sun shines. So our experiment would be run for it when helium is available. So those were the days when once you know your quota of helium is coming in, yes, we have to be in there. We used to stay back. Of course, initial days I used to stay in the hostel, but later after my daughter came in, I used to shuttle. But then there were periods when I used to stay. Once the liquid helium has come, yes, you have to start and finish the experiments. So those were the kind of experience which we had with these systems. So as you can see that these materials did have some very interesting properties at low temperatures, magnetic properties, and hence the need for this low temperature cryostat. So then later, as I moved on into the colleges, the research initially was with collaboration with TIFR and so on. But then, you know, it is always said what is being the contribution for the home institution. And among the various colleges I moved on, it was with Sophia College that I had a very long association. And that it is where I implemented a DST Women Scientist project, indeed, because that was a time of, again, the boom for nanotechnology. And particularly, we looked at nanoparticles for biological applications. Because in this institution, we did not have a physics major. But there was a very good research lab both for chemistry and life sciences, and especially in neurosciences. So what we did is associated with the biologists and started looking at magnetic nanoparticles which could have biological applications. In particularly trying to look at magnetically guided drug delivery systems. So it was implemented in 2005 for a period of 3 years, and very soon after 2009, I came into back to the department. So by that time I had finished this project. So some continuation in this is still going on. So it involved making the nanoparticles by chemical method, studying the structural and magnetic properties, looking at the biocompatibility. But the most important thing was what happened was there was a lot of interdisciplinary research between the chemistry and the biology departments with the physics department. And the students not only at the PG level, but we also had students from the undergraduate level. And that, I believe, was a very gratifying experience. So these were some of the results. I just show a typical one, CeFe304, which showed a super paramagnetic behavior. You typically know that this is a hysteresis curve in magnetic materials. You have a wide loop, but when they become what is called a super paramagnetic, the loop is width, the coercivity is near zero. And as you can see from the X-ray data, students will soon be doing some analysis on this, I hope. So the widening will indicate, is a measure by which you can measure the grain size, and we typically got 22 to be in the range of 10 nanometers and 40 to 50 EMU per gram of magnetization. So this is a signature of super paramagnetic behavior, which would render it useful for biological applications. And we did study some systems. And one important thing was, we always, the TIFR culture is build your own instrument. So there was this MH loop tracer, which is a PC-based system, and it has been developed by one Mr. Likite of, and he was incidentally an ex-TIFR person who has worked with Professor CRK Murthy, who was very well known for his work in rock magnetism. So they had, used to have a portable magnetic hysteresis measurement systems, and he had to just develop the electronics in order to be able to measure these signals from all the nanomaterials. And I think it was a reasonably good one, especially when you're initially making the samples, you want to know, before you can take it to elsewhere for high-ended characterization, because in a college we can't even look at the XRD. I used to come to the department, so we used to once this was set up, we could at least get, okay, this is showing a wide loop or small loop and so on. So for calibration, we had taken some standard samples, and it is still present at the college. And we acquired a similar system for the nano center, because Professor Kotari had visited the college, and he was very interested in this kind of thing, and with some additional attachments, if you want to go for high temperatures or low temperatures, even that, those systems are present today in nano center. So it's all automated. This is a sample holder which goes into this box, and you pass the, it is a pulse signal. After average of various cycles is taken, and it plots this, what you call as a moment versus the field. So the maximum field it could go was not, 5 kilo Austin, but it was good enough for all these soft magnets. So we could, with the project, we could also develop the lab on the whole, which is what was interacting with the biologists. And finally, what was most gratifying, as I said, these were all undergraduate students who did this project, and they displayed their exhibit in a intercollegiate exhibition, and they were awarded the first prize. And this was there were many, 2-3 batches of students, who continuously were able to work on this, do some of the experiments or the other. And it was a very, and it not only remained at the popular level, along with the biologists, we were also able to get some publications. And with this, soon I entered into, and for this I would thank, I had a collaborator from Kandivali Thakur College, who was actually doing this study on chick embryo. That was a very, and that work was continued, and one of my PhD students, Nuris, she did a lot of work on this for a PhD work. So this was so much for all the nanomagnetics. So there I have been giving talking a lot about it in various department meetings. So what I will now go for is the other part, the experimental technique, which is basically focused on teaching learning. I try to keep this, this was actually being used, when I was teaching at the college there. They did not have a major in physics. So they would always insist, try to speak in some language. Assume we just know the 12th standard science. So I try to address that. So maybe this also remains at that level, but I hope it will be I chose to remain at that level, because many of this time students say we are a little lost, we need to understand. So I think that what I start with here, some of the terms they must have done in their BSc. So with that, I think they would be able to catch on what is happening, and we very soon hope we will be able to do something good, no matter what, online or offline. My plan is always ready. That's why I've been asking, talking to Professor Anuradha Mishra as to what kind of scenario is it. So no problem, whatever it is, we will have something interesting for the students. Okay, so that is what I said, the quest, the rest, And finally, the best, the superconductivity, which always is of interest to the students. How many of you, all of you students, and even I'm talking to my colleagues, all remember this setup in BSc, where we look at this constant volume air thermometer. Okay, so you immerse this in a water bath, and then you have this mercury manometer by which you can measure the pressure, and as you heat it, record the temperature, you observe the change in pressure, and then you have this graph. So PV is equal to RT. So if your volume is constant, you have this P versus T graph. Okay. So what is done is just look at this graph and extrapolate it on the temperature axis, and you will see that it touches, the intercept is minus 273.15 degrees Celsius. Okay. And this was repeated for different gases. This is, of course, been done since all the from Charles Boyle or Gay-Lussac and so on. So what they found was this, and this essentially has been Lord Thomson, because those days they were using many of the different temperature scales. So what he did was, it was basically William Thomson or Lord Kelvin who developed the thermodynamic absolute temperature scale. Okay, so you can see this over here, minus 273.15, and this is where he said is your Kelvin. So you see the divisions in between are identical. It is just that there is a shift, okay, down by minus 273.15. So that is your absolute zero. And what happens at that? What happens to the various materials? So this has been the quest, first of all, to reach low. How low temperatures can we go? This 0 degrees Celsius or 273 degree Kelvin, we know, is your freezing, where water turns into ice. And then lower than that, you have the different gases, their boiling points being lower. And then as we liquefy the gases, they act as coolants, and you are able to reach those temperatures. You can have your experimental vessels and perform the experiments. So the challenge was to reach as close to this absolute zero as possible. So which were the elements that would go that low? So here again, as this is your absolute temperature scale. And as I told you, this is absolute 0 to 300. And that corresponds to your room temperature, 27, right? And when we go logarithmically, in generally the temperatures, see, most of our solar physics and all the stellar astro people will be looking at such higher temperatures. So the surface of the sun also, you're close to 10⁴ of a Kelvin. But the material scientists and general low temperatures, when we talk of, we are talking generally on this scale. Because liquid hydrogen, the boiling point is 20 Kelvin. So here we have nitrogen is 77 Kelvin, and liquid helium, as you know, is 4.2 Kelvin. So the quest was to go to as low, close to zero as possible, and the lowest temperature achieved today is the order of microkelvin. So there has been a journey, the historical development. There was a lot of these people. There were some more names. I just missed putting in Kapitza's name. So Lind, as you know, because at that time was also the, as you know, the industrial revolution. So as people developed different systems for liquefying the gases, very soon they would were also be able to upscale it. So as I was told again, today again, Professor Nagarajan, I recollected what was the kind of race which was there between James Dewar and Camelingons, because the challenge was up to hydrogen. Yes, it could liquefy at 20 Kelvin, but then the problem with hydrogen, as always, is because it's inflammable. So you would like to have something which is more safe. And in that sense, it was helium, the isotope helium-4. You have the other isotope helium-3, both of which can be liquefied, but then helium-3 gas is rarer and hence more expensive. Of course, helium-4 is also equally expensive, because main thing is procuring this is because it is rare. So the boiling point is 4.2 Kelvin. And then once they were able to liquefy this, then a lot of there was a shift in trying to develop all measurements using cryostats with the coolant as liquid helium. Now with 4.2 Kelvin, all of you are aware, if you want to reduce the boiling point of a liquid, what you do is you have to reduce the vapor pressure, yes, above it. And you pump over it, how you similarly make use of the reverse is in the pressure cooker, you increase the pressure to increase the boiling point. Similarly, the reverse, you have to reduce the vapor pressure above the liquid. And 1926, they tried doing this. You have a cryostat and connect a pump. So you will be able to pump down, I think 1.1 Kelvin is what they call it, but it's generally 1.5 Kelvin. Then there was another technique of going down to low temperature to millikelvin, and that was called the magnetic refrigeration or adiabatic demagnetization. You would have studied in the part 1 where you talked about when you studied magnetism and paramagnetic salt and getting low temperatures by cooling by a paramagnetic salt. So this is the technique is nothing but what is called as adiabatic demagnetization. I'll just briefly discuss this what is. And the next one is this, as I told you, the other isotope of helium, helium-3. That could go down to, because this is 4.2, this could reach temperatures up to 0.3 Kelvin. But only thing is you are limited by the cost. Then what people started working on was working with the mixture of helium-4 and helium-3. You have a mixture and it's almost somewhat, you allow it the mixture, allow it to expand. So you are basically diluting it into the system. And with this, this technique is called as dilution refrigerator. There's a multi-stage system, a quite a high-ended system, but you can go down to few millikelvin. Okay. And microkelvin has been also achieved by using, here we talked about adiabatic demagnetization of a paramagnetic salt. So there the spins that are involved, magnetism is coming in mainly because of the electrons, the conduction electrons which are available, that spin, you're dealing with the electron spins. Whereas if you start working with the nuclear spins, you will be able to go several order of magnitude lower and achieve low temperature. So this is what has been achieved in TIFRs. It is a multi-stage system. So I'll also show you the record. At least, of course, elsewhere, many of the places, especially after Netherlands and all those places, we have Germany. There is a whole list of labs where exclusively, low temperature work is being carried out. But we would like to know in our own country or in our own city, here in TIFR, this has been achieved. It was, I think, around 2011, 12, the work was on, I think, and very interesting results have also been produced in Professor Ramakrishnan's lab. So just to give you a brief, all of you know this is a refrigeration cycle. So what is involved is basically at the heart of it, you have a compressor with a working gas and the heat is dissipated by the coil. There is a condensation at high pressure and this flows through, and here what is the most important thing is the expansion valve, the Joule-Thomson valve as it is called, goes in, and this is your working space and it is able to cool the system. And depending on the further the design, you have a freezer or you have just to cool it at a certain temperature and so on. So this is a basic principle. I think all of you will be aware of the refrigeration cycle. So when you now have to liquefy gas, it is basically the design is this, and there are always some improvements. So you will see a lot of, when you look into some engineering books, you will see cryogenics especially, a lot of this. So when you talk about liquefaction of gases, so you look at TC, which is basically the temperature at which the liquid and gas phases coexist. And there is this effect which you would have heard of, Joule-Thomson effect. It is an irreversible process where work is done against the interatomic forces in the gas, and it is always used in the last cooling stage in liquefying the gases. And we talk about every gas as its inversion temperature. It is this temperature below which you cannot just produce Joule-Thomson effect. You have to at least go down below this inversion temperature. So all gas liquefiers basically have some kind of an expansion engine with followed by a Joule-Thomson stage. So this is a pictorial representation of what I have said. You will, of course, would have seen it in the net. And this is the kind of, as I told you, for every gas. So carbon dioxide, you know, very well know when we're looking at Van der Waals modification, you know, the same, you know, Andrews experiment with carbon dioxide, okay, where he was able to show the real equation of state for the real gases, what are the challenges. And for the various gases, you can see the boiling point. So this is where you will be at least close to this. So if you have a nitrogen as a coolant, you will be able to at least, if it's not 77, close to that, this is the lowest possible, you will be able to reach these temperatures. So it was for quite some time, helium was posing a challenge, mainly because of the Van der Waals forces. You know, it is a closed shell structure, and overcoming this was a challenge, and this is where Cameling-Ons managed to get ahead in the race of the others. And what I understand, as we were trying to understand what is it that helped him, is basically, maybe one thing is, okay, he was helium gas was easily more available to him, but it had a lot to do with On's entrepreneur skills as compared to all his contemporaries. So this I thought picked up was an article. I don't know, I'll share this reference. And these are also, this is Cameling-Ons you have over here. So you can see, you know, even in those days, he is, all these setups used to be really huge. And we used to be working with such glass cryostat, multi-stage, one inside. You know, you must be, this structure is similar to your vacuum flask. Only thing it is, you know, it is double walled. You have this glass sealed at the bottom. So you have multiple stages. You fill the liquid here, and then you have the sample space. And the kind of compressor which he used, you know, the mechanical movement and so on. So you will see, I find all this very fascinating. You know, ahead today we talk about getting a pump, but you just see the kind of creative design which they came up with. And today, if you say you're having a helium plant, you will see this kind of all this compressor stage. Of course, much of it is now electronically managed. But you see, these are the transfer lines. You liquefy it, and it is transferred from one container to other. And what is most important is that the gas, because once it is stored in the divar, there is always a constant boil off at the surface. And we don't, and when it is helium, of course, if it is nitrogen or something, what happens is there is always a relief valve so that if pressure builds, it can be released. But in case of helium, you need to have a recovery line so that it is collected back and goes back to the plant to be recycled again. So this is our Cameling-Ons. So Cameling-Ons, once he liquefied helium, it was not just his goal. What he was more interested was trying to see how he has been working a lot with all the metals, and he wanted to really see what happens to these metals at such low temperatures. And okay, before I could, because then we know that in 1911 was a classic discovery of superconductivity. So before I go over to that, since I'm still talking about the quest, I'll just briefly address this technique of adiabatic demagnetization. This you'll have studied, and students have done it in their part 1. So this paramagnetic salt was Debye and Gyauk were responsible for, and they used something cerium magnesium nitrate, which had it is antiferromagnetic temperature of 1 millikelvin. And there are various other salts that are used. Basically, they are paramagnetic. So what is done over there is the following. You know, if you plot the entropy, we say when something is disordered, the entropy is large. And when you try to order them, you know, paramagnetic material, salt spins are basically would be disordered. And when you apply a field, some ordering sets in. So we have this field here. So we are showing this as an entropy versus temperature. And you can see initially the field is off. So you are at this point, the paramagnetic salt. It is at a particular temperature. And then the field is turned on. When the field is turned on, more of the spins get aligned. So there is a drop in the entropy. Okay. And once it is, there is drop, the system is cut off. That is adiabatic. You know, you are, first of all, you're connected, the valve is shut so that this system is cut off from the surroundings. So whatever temperature and magnetic field it is in, it is trapped. So it is in an adiabatic state. And at this stage, the field is also switched off. So that is why it is two-stage. It is first pumping off, making the process adiabatic, and then switch off the magnetic field. So you are demagnetizing it. Once it is demagnetized, what happens? Again, it goes back to the state of entropy. But here, since it is already what happens in this case is the entropy curve, it moves to this, but in the process, there is a reduction in the temperature, because in order to do that, it pulls away the heat from the system. So hence a cooling is produced. So this in principle is a very simple pictorial representation of what is the process of adiabatic demagnetization. And again, very simply to put on, this is the ratio. All of you know that mu h by kT we always talk about. So the H or V is inversely proportional to T. So you have this, you know, this is the initial temperature field and final field. Similarly, here, initial and final temperature. So this is the ratio. So the final temperature would be decided by this. So if you are going to reduce the field, it won't go, if it go to 0, but it will go to some finite small value. And that is the temperature which you will be able to achieve. Okay. So this is the simple steps which I have outlined, so that I hope all of people from other areas would also be able to get a feel of what is meant by this adiabatic demagnetization. And with this, they were able to go down to millikelvin. I think in the TIFR setup, which was, I think, in the 60s, they had achieved temperatures of about 10 or millikelvin or so. Yeah, so this is one I was telling you, the dilution refrigerator, which makes use of the entropy of mixing of these gases. And then again, there is an adiabatic dilution, which leads to a fall in the temperature. And this experimental design was given by these scientists. And by 65, 66, we had, on a large scale, you know, commercially they were available, which could go down to 2 millikelvin. Okay, so the design is quite involved and high-ended. Okay, basically you can think of it, it is separating these isotopes by a process of distillation at different vapor pressures. But in order to begin this, you have to bring the system first to a temperature of 1 Kelvin, which is achieved by your usual process of having liquid helium and reducing the vapor pressure. And then you have this stage introduced. So this, as you know, is a phase diagram of the, and that's why it looks, this is called as a lambda curve. So this is like your tri-critical point. And another thing about this helium is its property of superfluidity. So below the critical point, both whether helium-3 or helium-4, I don't recollect exactly what is the temperature is, I think around 3 or something below their boiling point, they turn. And what is superfluidity? Superfluid meaning all fluids, they have a certain viscosity. So, you know, if they are in a liquid, they have to be still. But when they are helium below this critical temperature, what happens? They actually flow out as if they defy gravity. So this is behaves as a superfluid. So that itself is a area of interest. And this is where we say these are all quantum phenomena being manifested on such a macro scale. Besides superconductivity, also we know is basically condensation of all the electrons into pairs and forming a very coherent state. Similarly is also the property of superfluidity of helium. So this is how all these dilution refrigerator, which I referred to, this is basically the cryostat having multi layers of all the insulating material, and inside would be the sample space. So any kind of transfer of liquid and so on would all be happening through these ports. Okay. So this is how it would look at. Look, as I told you first, there is a stage which goes to 1 Kelvin, and then there are a lot of heat exchangers, and finally you have the mixing chamber, where this is where you would get the millikelvin using what is called as a dilution. And just to put in this, the microkelvin facility at TIFR, so here, this I think they were able to not only they were using this, they were also using the nuclear, using copper, okay, and platinum. For the question that also I'm coming to, once besides reaching the temperatures, the most important thing is we talk about we have reached this temperature, but how are you going to measure it? Surely not with a mercury or any other thermometer that we are familiar with. So at such low temperatures, you have to rely on looking at the nuclear spins. And of course, one is the nuclear spins and the other one is looking at NMR. Because when you look at the NMR signals, it is very sensitive to temperature, very small shift in it at such low temperatures. The shift in this is going to be proportional to the temperature it move, and then at such low temperatures, they use NMR thermometry. There are some particular isotope, there is platinum and copper or whatnot that is being used, and they have been able to go down. So they were able to cool 5 kilogram of copper down to 39 microkelvin, and it remained there for almost 36 hours. It was really a major achievement by Professor Ramakrishnan and his group. So you have, again, it is a multi-stage. First, you have a dilution refrigerator, which I talked of, which would go to 10 millikelvin. And then there was this copper foils, which would act as heat exchangers. And here was a small superconducting magnet as a switch. And finally, this big copper block, which we talked of, for a very high purity copper, just called OFHC. It's not just your normal copper, very high purity, very expensive. And then this block of copper, they were able to cool the nuclear spins. And then, of course, you need to have this superconducting magnet for the process of nuclear adiabatic demagnetization process. So it is a multi-stage facility, and the temperature produced here was in the order of microkelvin. So I think, of course, sometime last year there were a lot of. I'm sure there would be also videos which would be available. I think it would be interesting to at least to familiarize yourself with such interesting achievements that we have in our own in our neighborhood. So this is the team, and this is Professor Ramakrishnan, my talked of. So you can see all the gigantic systems that they have. Okay, it goes down right down to the basement, the huge magnet, the multi-stage system they have. And what was very, so again we said, okay, you go down to low temperatures, what was being studied. And this is where I talked of, at this stage somehow I'm not able to open the link here, but since it would be saved, I'm sure we'll be, because I wasn't able to open it, that it showed bismuth. Bismuth, is very close to lead, 82, I believe, the atomic number. And it is referred to as a semi-metal, because in metal, that there are overlapping conduction and valence bands, whereas all semiconductors, you have a gap. Bismuth is said to be metal where the bands don't overlap, you are just available, they close in. So the amount of conduction electrons is limited as compared to the density that you would have in metals. But nonetheless, it shows some very interesting properties. So normally, you would think that most of the conventional superconductivity is observed in mostly metals or metallic alloys. So nobody would think that, of course, that is the same thing which happened with oxides also. There the process is different, but in bismuth, it was very interesting to see that it was superconducting, and that too at, but of course what was required was a single crystal, which they again had grown at TIFR. And it was, and sometimes you need to put an additional pressure in order to observe superconductivity, and this was observed at ambient pressure. So this is another very big achievement, and I've been telling, because bismuth we were doing in the lab, when you to look at it, it just looks like lead. What we were looking at is the magnetoresistance. I'm not going to bring in over here. This is a lab experiment which our students are doing. But what is interesting was, this is recent in the sense, was in 2016. Again, in the Professor Ramakrishnan's lab, with the low temperature facility they have developed. So next is, yes, what is the paraphernalia? When you talk, we achieve low temperatures, how are you going to measure it? So you talk about different, kind of thermometer. One is, you talk about primary thermometers, which means, it is like, you can say absolute. So if you have an ideal gas, PV is equal to RT. So if you keep one of the two, you can either have a constant pressure or constant volume thermometer. You will be able to measure the temperature. Of course, black body radiation is something which they normally use for measuring higher temperatures. But then you have the spin system, spin paramagnetism, which because of that mu h by kT, you will be able to, that is the kind of relation you will be able to see. And especially in nuclear spins, the measurement is very accurate, because they are very sensitive to a small change in the temperature, and hence can be used for monitoring or measuring the temperature. Whereas the secondary thermometer, now liquid and glass is what we all use, the mercury thermometer which we use. Of course, of late we are also using the resistance thermometer, whether they are semiconductors or whether they are metals. You only changes that if it is a metal, then it has a positive coefficient of resistance, temperature coefficient of resistance, whereas in semiconductors it is the other way. And of course, a very old one is your thermocouples. So these are, and they all function in different ranges. So when you go to, I think, lower temperatures, when we go initially, I think a platinum thermometer would function down maybe up to 100 Kelvin or so. But if you want to go lower, maybe even to liquid nitrogen temperature, you can safely use the platinum resistance thermometer. But lower temperatures, what is preferred is semiconductor. You use the silicon diode sensor, and then there are more. And here there is a lot of materials that have come up. And but at very low temperatures, a microkelvin or millikelvin that we talk of, there what you use is you make use of these spin dependent, or you are looking at NMR thermometers. Okay, so this in short is how temperature is measured for different ranges. So finally, this also is, I would say, because there is a close linkage. So, all magnetism comes in because of the inherent spin property of the electron. And we living on this planet Earth, we all know that it has its own geomagnetism. It is our own huge magnet, which is many of our colleagues are aware of, who are studying all the space physics and so on. So there is all this magnetic field associated with the Earth. So there is some kind of an analogy, which is a very interesting cartoon, I thought. And so you are looking at the north and south poles. So this was, and one thing about magnetism, it was magnet as such was discovered even before electricity was, goes down to 3 just centuries ahead. Of course, people talk of a story of lodestone and all so on and so forth. But the idea is that these materials showed this property. One was it's attracting the iron-like objects, and the other thing is the directionality, always pointing towards along the north, so geographic north-south. So there were, Gilbert was the, I would say, was the first to come up with a treatise to bring them all together. And then, of course, Ørsted's experiment established the linkage between electricity and magnetism. And people developed the electromagnet. And the first time, because iron, it is not just, we know that it very small field, it gets magnetized, shows a large saturation magnetization. But what is interesting is when it is reversed, it shows a hysteretic effect. Okay. And then you know that it is dependent on temperature. Beyond a certain Curie temperature, it loses its magnetic property. From a ferromagnet, it becomes paramagnet. Then we had all the theories coming in. But soon it was known that, yeah, magnetism, the origin is quantum mechanics. So this is in basic, summarizes what are the quantities. So basically, when you say you are producing a field, you are looking at applied field H, which is proportional to the current you pass through the coil. That is the simplest magnet that you think of. And you produce the magnetization is induced in, and you call this the magnetic induction, where this is your mu naught, the permeability of free space. Okay, so this is a basic equation. And the associated quantities that we look at is, we look at the susceptibility. Then that this is how we define it, is basically the change in magnetization to applied field, and the extent to which a material is permeable to magnetic field is referred as the permeability there, which is the ratio of change in the induction. Okay, so these are the quantities. So when you look at the susceptibility, you say whether the material is magnetic, paramagnetic, ferromagnetic, or so on. So this is the simplest. Of course, you have the lodestone, you have the bar magnet, and so on. But this is the measurable magnet. You have a current carrying coil. The would produce a field at the center, which you followed by the right-hand rule. So this is your simple solenoid magnet. And electromagnet is nothing but you insert a permeable material, something like a ferrite rod into it. Because it has got a high permeability, it produces much larger fields. Right? So this is your electromagnet, the north and south pole, and this basically consists of the coils. And when you are passing higher currents, you also need to cool it. So you have a water cooling coils and so on. But the highest fields that you can get with an electromagnet is not more than 2 Tesla. Of course. Now what we have is, we have permanent magnets where we make use of rare earth based system NdFeB, which gives you close to 3 Tesla. And of course, finally, for the high fields that we talk of, this is where we use the superconducting magnets. And another thing about magnetic materials is they depend upon the ordering. You talk about the 5 different kind of basic ordering, or you can classify them based on the structures or the applications. So I'm just giving you some kind of introducing you to this you are all familiar with. So the ordering can be ferro, antiferro, or ferri. And then you talk about dia and paramagnets. So the reason why I touch upon this is because very soon when you're going to talk about superconductivity, there is a very interesting thing about superconductor. So that is why, and paramagnet, of course, we just saw the application of paramagnetic salt in some of them being able to produce, used for producing very low temperatures. Okay. And then, of course, based on the structures, you talk about whether they are single crystal or polycrystalline, or they are amorphous. And finally, with the nano coming in, we are looking at nanostructured materials, which show a totally different behavior. Yeah. So finally, these are the classification based on, so some of these effects are which we have measured. Magnetoresistance was what I was talking of. Some of my PhD students has worked on the magnetostrictive property and then the magneto-optic property. But I think we are running short of time. I'm not going to spend too much time. I'll quickly go through. Finally, the most interesting, as I said, the best is discovery of superconductivity, which was an unanticipated effect. So this was basically said camelling ons. We liquefied helium And what he did was he was measuring the resistance of a specimen of mercury, and he found that there was a sudden drop of several orders of magnitude. Initially, he thought there was something wrong with the system, and you must be knowing the story, but this happened at a temperature of 4.2 Kelvin, as if it lost all its resistance and became a perfect conductor. Okay, the zero resistance. But then it was superconductor is not just a perfect conductor, it is also a perfect diamagnet. And that, as you all know, is what is called as a Meissner effect. So when you say you have very near zero resistance, it will have a high current carrying capacity. So if you carry high current, you can generate really high magnetic fields in the coils. But in addition to this, these you have a critical temperature above which it is goes to normal state, but it is also limited by a critical field and as also a critical current density. So you can basically show this if you plot a field versus temperature. Above this critical temperature, it is normal, and also as we reduce the temperature, it goes to this critical field, above which again it will go to a normal state. Okay, and if we measure the resistance as a function of temperature, for a metal, it goes down in this behavior. You see for a superconductor, it drops at the TC. So this was your Meissner effect, which is pictorially represented in this form. You say that basically the point is that it is history dependent here, whether you are going to cool it in zero field or you apply the field and cool it. And then when you switch off the field, you will see that in this case, it depends on the history. So if it was in zero field, there is no flux trap. Whereas if it had the field, there are the flux lines trapped. This would what happen in a perfect conductor. But when we have a superconductor, what happens? Irrespective of whether it was cooled in zero field or applied field, the flux, once it is cooled below the transition temperature, it always shows expulsion of flux. This is your Meissner effect. So let me just quickly browse through. This is a textbook thing you must have heard of. It is basically these type 2 superconductors which render themselves useful for making superconducting magnets because they have a very high critical field. Okay. So these were some of the superconducting materials. Till then, all the known materials, they had a critical temperature of 23 Kelvin. These are some of the classes of materials. But it was in around 84 and 86, 87 when it was Bednorz and Mueller who discovered superconductivity in a cuprate, that is, they are oxides. Then you had this YbCO and later the bismuth. And so this is typically 125 to 150 Kelvin is the highest temperature, I believe, which is meaning they have to also be stable. So this is the record which was achieved. And the advantage is that because they are above 77 Kelvin, the coolant which you use can switch over to liquid nitrogen. You don't need helium. So in that cases, it is cost effective. But the problem here is because these are oxides. So unlike your metallic elements, you cannot draw them into wires and make coils. So there we still rely on your conventional metallic superconductor. So this is how they show the graph of the transition temperature. So the highest reach till today, it was the scenario 90, and even now I think it has not gone much beyond this. So this is the temperature range wherein you can, above which you can start using liquid nitrogen. So these were the era till when you have confined, and these were the niobium alloys are the ones which were widely used for making a superconducting magnet. So this is how it would look like, all the electronics, the cryostat, and you immerse the whole coil into this. And you know that all your MRI magnets, you talk about the superconducting ones, high field, 12 Tesla, and so on. So this is where the coil is inserted, and then you have the patient whose MRI imaging is done here. So one place where superconducting magnets are used. So this I show is the system that we had done during my PhD days. So here you can see is, it looks like your reel where you put the while flying kite. But here, you know, you have to be very careful while you wind the wire onto this former, because if it develops kinks, it has to be in a uniformly wound. And to tell you that I think over a period of 3 weeks, we wound this. Yeah, Professor Nigam had already made earlier some couple of magnets. This was, I think, the third one that he made, which was designed to give 7 Tesla, but I think it went close to 6 Tesla. And these are all the lead connections. And what happens is this whole system is immersed in the DIVAR, double wall DIVAR, which is because this magnet has to be totally immersed in liquid helium. Because once the level starts dropping, then that part of it becomes normal, and the field will start falling. So that itself is in itself. So we had developed this, and then there was a VSRP who came from IIT Kanpur, who also made some more magnets. And incidentally, all of know about Dr. Deshdeep. So he had tied down with this student, Anjan Gupta, and had developed all the various instruments that he talked of, the tunneling, my STM, and so on. So this is a cartoon to show the kind of fields. Yes, at the poles, are you having a superconducting magnet? So I just picked it up from here. And so you see the innate linkage, low temperature physics. One is, of course, it led to the phenomenon of superconductivity, which helped in developing high field magnets. And finally, yeah, how much time do I have, Nanish? Hello?
Yeah.
How much time? You see here, this is a pellet of a high TC superconductor, YBCO, which is cooled in liquid nitrogen. And when you try to float a light magnet, try to bring it close, because of this Meissner effect, it repels the flux. And for, there is a certain distance, you can actually see that it floats. You can see this. Again, this is the link where you will be able to see this levitation. Somehow it is not working, but you can note down and see this. And another thing is, as you remove the liquid night cooling, slowly, it doesn't just abruptly fall, it slowly falls down. So this picture, I think some of you must have seen at TIFR, where they demonstrate this levitation, because it's easier to do it with the high TC magnet, because you need to use only liquid nitrogen. Okay, and then we did a lot of, in those days, my association was with the college students, where we used it for making some high temperature superconducting pellets. There was students from National College who actually tied up, and Professor Nagarajan was again the guiding force. And we did some kind of experiments then. Okay. And I think even some of our MSc students in the old annual system, they had also made some of this superconducting pellets. So this is in short, I would like to say, it started with, one is for Rosen's, and of course I forgot to mention Lunasma's book. And superconductivity, this is a very nice monograph that we have. So these are some of the early day books which I read, and even still today, I think it is very relevant to it makes a good reading. Okay, so this I'll end it on a lighter way. Instead of just putting a thank you slide, end it on a lighter way. This was a cartoon shown by a scientist who gave a talk in TIFR during those superconductivity days. So this is a conductor. I call this a semiconductor, and this is a superconductor. So with this, I stop my discussion there, because as I said, I just was been sharing. It was a teaching learning experience about not only just the quest for zero, but what has been the spin-off. One thing is your superconductivity behavior, and all the other discoveries which follow. So I will stop here and leave the field open for any discussion or questions.
Like your superconductor superhero. It matches well with magnet to superconductors, really good. So thank you, madam, for sharing all your knowledge about moving towards zero and how important it is for the superconducting materials. So thank you for it. So session is open for the question and answers. So if you want to ask question, you can just unmute yourself and ask directly.
Can you hear me, Nagarajan here?
Yes, sir. Yes, sir.
Okay. Since Radha mentioned about the
Ah.
levitation matter,
Ah.
we have in CBS an imported superconducting pellet, which I can show the levitation.
Okay, sir.
More interestingly,
Hmm.
I can also show the superconductor attracting.
Okay.
Everybody will keep on saying repelling.
Yes.
I will show you attraction.
Yes.
So whenever the SSP
Huh.
course runs and you are on superconductivity,
Yes, sir. We'll
please
have the
contact
demo.
me.
Yes, sir. So, yeah, again, it's not confined only for SSP. We would like to show it to all our MSc students in whichever best way possible. Maybe if it is online, fine. We will have the video taken and share it with you all for a start.
I noticed that Nyayata is also
Huh.
in the participating bunch.
Huh.
You catch him also.
Yes, sir. Definitely. Yeah, I can see our friend Dhar is also there. So, yeah, we have our team. We can come together to arrange some of these demonstrations. Yeah.
This can be a good part in refresher courses, especially when where teachers are also very interested to see such experiments, and they can also set it up in.
Yeah, we did it in 2011 when both Mr. Srinivasan of the helium plant, he and Vijay Arolkar, they had both come, and now Arolkar has apparently put up a lot of uploaded many of these videos on YouTube. So he says if you just Google with his name, you will be able to see many of, because he not only stopped at this level, he also showed a working model of a train, with a set of magnets. And incidentally, one of some of a batch of our students, they actually went to him. They tried to at least able to understand, but then okay, I think somewhere we got stuck. We could not procure the magnets on time. But the other part of measuring, using the sensor to measure low temperature. So they actually brought the liquid nitrogen. They had set up a small stand on a plastic to mount the sensor. So our students got the feel of building their own instrumentation. And let me tell you, these were all our MSc students. I just over the last few years, there have been a lot of interesting projects which students have done. And this was one of them.
If no one has the comment,
Yes.
I have one more.
Yes, sir.
The know-how from UDP.
Huh.
Is Rangwala Sahib around?
I thought he was there. Huh.
Anyway,
Huh.
he gave me a beautiful book called
Huh.
Art of Experimental Physics.
Right.
There is one chapter, perhaps the first chapter,
Uh-huh.
on pulse transmission in coaxial cable.
Yes.
It's a very enchanting, simple experiment. I keep enjoying it with my students. I strongly recommend that the UDP also should do that.
Yes.
Again, the know-how is available.
Yeah.
If anyone wants.
Right.
But as I said, the origin is UDP.
Yeah. And especially the onus is now on the students. We will try to motivate them, and we'll presume, okay, let us first assume that we will have to go for an online thing, so that whenever we are able to come hands-on, that will be there. But we should be able to develop the online tutorials.
So there is a comment from Professor Manohar Nyayate.
Yeah.
He says, thank you for remembering me, Professor Rapid Nagarajan.
Yeah. Rn. Yeah. I don't know how much of it, Nanesh, do we have in the experimental